Meet Enceladus. It's the sixth largest moon of Saturn, a small icy world circling a giant planet, and honestly, at first glance, it doesn't look like much. But don't judge it by its size. When the Cassini spacecraft spotted enormous jets of ice and water erupting from its south pole, it stopped scientists in their tracks. What was causing this? Flying straight through those icy plumes gave us some answers. Cassini found water, organic molecules, and strong evidence of a hidden ocean, possibly with hydrothermal vents warming it from below. Then, in 2017, Cassini ran out of fuel and was deliberately steered into Saturn's atmosphere, burning up and taking our only close-up window into Enceladus with it. That left us with a pile of open questions. Is there really a global ocean under that ice? What's actually happening beneath the surface? And could this small moon actually support life? Nearly a decade later, we haven't sent anything new to Enceladus, but the research never stopped. The James Webb Space Telescope has taken a look, and scientists are still combing through the mountain of data Cassini beamed home. And it turns out we've learned a lot more than most people realize. Let's dig into this frozen world, the surprising chemistry hiding under its shell, and why data collected 10 years ago is still rewriting what we know about the search for life beyond Earth. Enceladus is only about 500 kilometers wide, roughly the size of the state of Arizona. It orbits Saturn at a distance of nearly 238,000 kilometers, where sunlight is faint and temperatures sit around a brutal -201 degrees Celsius. Because it's so small, cold, and dim, it was incredibly hard to spot. William Herschel finally discovered it in 1789, using the largest telescope on Earth at the time, an instrument he and his sister Caroline spent over a year building and polishing by hand. Even with that giant scope, Enceladus just looked like a plain, boring ice ball. That blurry first impression stuck around for almost 2 centuries. Everything changed in the early 1980s when the Voyager probes flew past Saturn. Instead of a dead, cratered rock, the images showed patches of surface that were smooth and strangely free of craters, a sign that something had resurfaced the moon relatively recently. Even stranger, Enceladus sits right inside the thickest part of Saturn's E-ring, hinting that the moon itself might be supplying material to that ring. Was this little world somehow active? Those Voyager mysteries were a big reason NASA and the European Space Agency built the Cassini-Huygens mission. Cassini launched in 1997, swung past Venus twice for a gravity boost, and arrived at Saturn in 2004. Over the years it produced thousands of scientific papers, but nothing caused more excitement than what happened during its earliest flybys of Enceladus in 2005. Cameras caught massive geysers blasting out of the South Pole, spraying around 250 kilograms of water and ice into space every second at speeds over 1,000 kilometers per hour. Enceladus wasn't just active, it had its own thin atmosphere. That discovery changed the whole mission. NASA sent Cassini diving just 50 kilometers above the surface to fly directly through the plumes and sample them, because these jets were the best chance we had of detecting signs of life somewhere other than Earth. So what does detecting life actually require? Scientists look for 4 things: liquid water, an energy source, the right chemical ingredients, and enough time for chemistry to get complicated. Enceladus clearly had water, that much was obvious from the plumes alone. The real question was how much, and where it was coming from. Early infrared images from 2006 showed unusual heat pouring out of the South Pole, right along a set of long cracks nicknamed the Tiger Stripes. For years, researchers assumed the ocean underneath was small, shaped like a lens tucked under just the southern region. But by tracking the moon's wobble, its libration, over roughly 7 years, scientists realized it was rocking back and forth far more than a small local ocean could explain. That meant the icy shell wasn't locked tightly to the rocky core underneath. The only way to explain that wobble was a global ocean, one that wraps entirely around the core, not just a pocket near the pole. Then in 2025, a team from Oxford, the Southwest Research Institute, and the Planetary Science Institute went back through old Cassini heat data from the North Pole, comparing readings from its winter in 2005 to its summer a decade later. They found the North Pole was leaking heat too, about 7 degrees warmer than models predicted. That told us Enceladus is producing more internal heat than anyone assumed, and that its ocean has likely existed for a long stretch of time. But here's the puzzle: this moon is freezing, roughly 200 degrees below zero on the surface. Water has no business staying liquid out there. So where's the heat coming from? If it were just leftover radioactive decay in the rocky core, like what warms Earth's interior, it would only produce about 1% of the heat Cassini actually measured. In 2017, a research team led by Gail Choblet proposed an answer. Enceladus is tidally locked to Saturn, always showing the same face to the planet, and that constant gravitational tug flexes and stretches the moon, generating friction and heat deep inside. But heat alone isn't enough, it has to travel from the rocky core up into the ocean. The theory is that ocean water actually seeps into the porous, silicate core, gets heated there, and then rises back up in narrow, focused plumes, essentially acting like a network of hot springs scattered across the sea floor near the South Pole. In 2022, a study led by Wayne Khan added more weight to this idea. By modeling the salt content of the ocean using Cassini's data, the team found the water is just slightly less salty than Earth's oceans, which strongly suggests ongoing or past chemical reactions between water and rock. In other words, hydrothermal vents. That matters a lot, because on Earth, hydrothermal vents are considered one of the leading candidates for where life actually began. There's a real-world example that helps put this in perspective: the Lost City hydrothermal field in the Atlantic Ocean, first discovered in 2000. Unlike typical volcanic vents, Lost City is powered by a chemical reaction between seawater and mantle rock called serpentinization, and it's been continuously active for well over 100,000 years, producing hydrogen and simple organic molecules the whole time, with no sunlight involved at all. Scientists studying Enceladus now treat Lost City as the closest thing we have on Earth to a working model of what might be happening under that ice. If Enceladus really does have vents like that, it checks off box number 3, the chemical ingredients for life. Cassini's mass spectrometer, an instrument that identifies molecules by weighing their ions, detected hydrogen during its flybys, along with more complex hydrocarbons containing carbon, oxygen, and nitrogen. Unfortunately, scientists barely had time to start digging through that data before Cassini's mission ended in September 2017, deliberately crashed into Saturn to avoid contaminating Enceladus or Titan with any hitchhiking microbes from Earth. Even after the spacecraft was gone, the discoveries kept coming. In 2018, researchers confirmed ring-shaped organic molecules and simple oxygen compounds in the plume data. Then in 2022, scientists finally spotted phosphorus, the last of the 6 elements considered essential for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sometimes remembered by the acronym CHNOPS. With that discovery, Enceladus had officially checked off every basic chemical requirement. It turns out the story had more chapters left, though. Some of Cassini's original mass spectrometer readings were tricky to interpret, because slamming into ice particles at over 60,000 km/h breaks molecules apart very differently than gently analyzing a sample in a lab. How a molecule fragments changes its signature entirely, similar to how cutting a fruit with a knife leaves different pieces than blending it. A team led by Nozoya Kawaya, using better analytical techniques and focusing on the freshest possible plume samples collected just 20 kilometers from the surface, published new results showing molecules more complex than anything found before: carbon dioxide, carbon-rich compounds, ring-shaped esters and ethers, and various nitrogen and oxygen-bearing molecules. This is genuinely complex organic chemistry, exactly the kind of chemistry that, in laboratory conditions, can start behaving in ways that mimic evolution. That leaves just one last requirement: time. Has this hydrothermal activity been stable and ongoing long enough for anything resembling life to actually develop? Cassini only observed Enceladus for 13 years, nowhere near long enough to answer that on its own. That's where the James Webb Space Telescope stepped in. Using about 10 hours of observation time, a team led by Geronimo Villanueva discovered a plume far bigger than anything Cassini ever recorded, stretching out to roughly 20 times the size of the Moon itself. This also solved a long-standing mystery about where the water in Saturn's upper atmosphere comes from. Enceladus is continuously feeding a massive ring of ice particles around the planet, making it the only moon known to directly influence its host planet's atmospheric chemistry. Those ice particles do something else too. As they drift through Saturn's magnetic field, they lose electrons and become charged, generating enormous plasma waves called alphenwings that stretch for hundreds of thousands of kilometers, connecting the moon to the planet and even bouncing back to create a strange lattice of plasma around Saturn. Scientists are still working out exactly what these mean. As for the longevity question, a recent reanalysis of Cassini's old infrared data by researchers Georgina Miles and Carly Howard found that the heat radiating from the surface closely matches what models predict the core should be generating. That's a strong hint the moon's ocean has been around for a long time and isn't just a brief, temporary phase, which is exactly the kind of stability life would need. What's remarkable is how much of this came from simply revisiting old data with fresh eyes and better tools. Even amateur astronomers have gotten in on it. In 2017, Ted Stryk went back through decades-old Voyager images and spotted what looks like a water plume that nobody had noticed before, a discovery that, if it had been caught earlier, might have completely changed how Cassini's mission was originally planned. Looking ahead, several new missions are in the pipeline. The European Space Agency is developing a mission aiming to launch around 2042, arrive at Saturn in the early 2050s, and possibly attempt a landing on Enceladus later that decade. Before that, ESA's JUICE mission, short for Jupiter Icy Moons Explorer, is already on its way to study Europa, Ganymede, and Callisto starting in 2031, specifically looking at how habitable worlds might form around gas giants. NASA's Dragonfly mission will send a drone to explore Titan's thick atmosphere. There's also a proposed German mission called Enceladus Explorer, which would use a heated probe nicknamed the Ice Mole to burrow through the ice and sample untouched pockets of the ocean directly. If any of these missions find even a hint of biological processes at work, it would mean habitable environments might be far more common across the galaxy than we ever assumed, tucked away inside small, icy moons that don't look like much from the outside. Enceladus went from a fuzzy dot that Herschel could barely make out, to a moon that might be one of the best places in the entire solar system to search for life. And the wild part is, we're still finding new clues in data that's already a decade old. There's a good chance the most important discovery about this little moon hasn't been made yet, it's just sitting in an archive somewhere, waiting for the right person to look at it in a new way.